Welcome, focus learners, to today's explainer. I'm absolutely thrilled to be your guide today as we unlock the physics of a sound wave, straight out of your Grade 9 science material. Whether you're gearing up for a big exam or you're just kind of curious about how we actually hear the world around us, you are definitely in the right place. We're going to take the whole complex science of acoustics and break it down into a really clear, fun journey. So let's get into it. Here's a quick look at our roadmap for today. We'll start with production, then propagation, dive into wave characteristics, take a tour of the human ear, explore ultrasound and echolocation, and finally wrap the whole thing up with a solid summary and some exam prep. All right, Section 1, Production, Making Sound. Okay, let's dive into this. To really understand sound, we kind of have to start at the very beginning, the actual birth of a sound wave. To kick things off, I want to hook you with a thought experiment right from the source material. Picture this. 2 astronauts are doing a spacewalk, right? They're out there repairing the metal arm of a space station. Now, when they strike that metal with their tools, can they talk to each other and hear the clanking just like they would back down on Earth? Hold on to your answer for a bit, because we are absolutely going to solve this mystery by the end of our propagation segment. So, the absolute fundamental rule of acoustics is that all sound begins with a physical action. Whether you're striking metal cymbals like the taal you're seeing here, plucking a guitar string, or even just using your own vocal cords to speak, you're initiating a physical disturbance. Basically, you're making something move. And that movement has a very specific scientific name. It's called a vibration. Formally speaking, a vibration is the periodic to and fro motion, or oscillations, of an object. Think about a stretched rubber band. When you pluck it, it looks all blurry, right? That's because it's moving back and forth so incredibly fast. As long as it vibrates, it produces sound. But the very second that vibration stops, the sound stops. That is the golden rule of sound production. Moving right along to Section 2, Propagation, how sound travels. Now that we've actually created a sound, how on earth does it get from that vibrating object all the way over to your ear? Let's trace that journey. Okay, before we go any further, we really need to bust a massive misconception. A lot of students think that when a source makes a sound, it literally shoots air particles all the way across the room and into your ear. Total myth. The fact is, the particles of the medium, whether that's air, water, or the solid wood of your desk, they just vibrate in place. It's like a domino effect. They bump into their neighbors who bump into their neighbors, passing the disturbance along. So it's the energy that travels forward, not the actual particles themselves. So let's pause for a quick, interactive pop quiz. This is based directly on a question from your textbook. When sound travels from a vibrating tuning fork across the room to your ear, what is actually reaching your ear? Is it the air particles? Is it pieces of the tuning fork's material? Think about what we literally just talked about. If you guessed energy, you hit the nail on the head. What reaches your ear is the energy carried by sound waves. See, sound is what we call a longitudinal mechanical wave. And that word mechanical is super important because it means it absolutely requires a physical medium to travel through, which, if you remember, finally answers our astronaut question. Space is a vacuum. There's no air. There are 0 air particles to bump into each other and pass the energy along. So no way, those astronauts cannot hear the metal clanking. Let's jump into Section 3, Characteristics of Sound Waves. Now we're going to build a sort of physical fingerprint of sound. When scientists map out a sound wave, they look closely at its mathematical characteristics. Here are the key definitions you're definitely going to want to memorize for your exams. A sound wave creates areas of high density, which we call compressions, and low density, called rarefactions. First up, wavelength. This is represented by the Greek letter lambda. Actually, as a quick memory trick, lambda looks a bit like an upside-down wave crest itself. It's simply the physical distance between 2 consecutive high-density crests. Then there's frequency, represented by nu, which kind of looks like a sharp V vibrating really fast. Frequency is how many of those waves pass a certain point in 1 single second, and it's measured in hertz. Finally, we have amplitude, which is basically how intense that wave is. It's the maximum change in density, and it's what determines how loud the sound is to us. So, the absolutely crucial point here is this golden formula right in front of us, the wave equation. The speed of the sound wave, v, is equal to its wavelength multiplied by its frequency. It's that simple. If you know how long a wave is and how many of them are happening per second, you know exactly how fast that sound is traveling. And speaking of speed, sound doesn't actually always travel at the same pace.
Because sound fundamentally relies on particles bumping into each other, it travels the slowest in gases, like air, at about 344 meters per second, simply because the particles are spread pretty far apart. But in solids, where particles are packed super tightly together, sound zips through there up to 15 to 20 times faster.
All right, section 4, the human ear. So, this traveling energy disturbance we've been talking about finally arrives at your head. Let's take a look at how our bodies are biologically engineered to receive it. Honestly, human anatomy is an absolute marvel. Think of the ear as this incredible, complex conversion machine. The sound wave funnels in and hits a very thin membrane called the eardrum, forcing it to vibrate. These vibrations are then amplified by 3 tiny, tiny bones in the middle ear. Finally, they reach the cochlea, which is shaped exactly like a little snail shell, and this performs the ultimate magic trick. It converts those mechanical vibrations into electrical signals that rush straight to your brain. And then your brain translates those electrical pulses and goes, ah, that's my favorite song, or ah, that's my alarm clock.
Next up, section 5, ultrasound, infrasound, and echolocation. But here's the thing, humans can't hear everything. Our ears are tuned very strictly to frequencies between 20 Hz and 20,000 Hz. So let's explore the invisible extremes of the audio spectrum that we are entirely missing out on.
Down below 20 Hz, we have what's called infrasonic waves. These are massive, deep waves produced by things like earthquakes and severe storms, and they can travel huge distances through the Earth. On the other end, above 20,000 Hz, we have ultrasonic waves. These are extremely high-frequency waves that bounce off objects beautifully. We use them in medicine, like for ultrasonography, to safely see inside the human body. And out in nature, bats use these ultrasonic bursts to navigate and hunt their prey in pitch darkness. It's an amazing biological process known as echolocation, and it's basically a superpower. And we made it to section 6, summary and exam prep. We've covered a ton of ground today. Now it's time to lock all this knowledge in with our final segment, completely designed to get you ready for those upcoming tests. All right, take a mental screenshot of this summary. This is your rapid-fire cheat sheet for Chapter 10. Let's recap. Remember, sound equals vibration. It is a mechanical wave, meaning if there's no medium, there's no sound. The energy is what travels. The particles just jiggle in place. Your master equation you need to memorize is velocity equals wavelength times frequency. And finally, human hearing sits strictly in that 20 to 20,000 Hertz pocket. Now, let's put that knowledge to work with a classic exam question straight from your textbook. Imagine a ship sends a sonar signal down to find the ocean's depth. The sound takes exactly 4 seconds to return. If we know the speed of sound in seawater is 1,500 meters per second, how deep is the ocean right there? Take a second and try to calculate it. Okay, here is the ultimate trick to every single echo problem you will ever face on a test. First, you just calculate the total distance the sound traveled using distance equals speed times time. Easy. 1,500 times 4 is 6,000 meters. But wait, that's the distance the sound traveled all the way down to the floor and then back up to the ship, so you absolutely must divide by 2. The true depth of the ocean is 3,000 meters. Do not forget to have the distance on an echo problem. It gets people every time. As we wrap up this explainer, I really want to leave you with this thought. Sound is just so much more than what we can hear with our own 2 ears. Scientists are literally using sound right now to listen to microbes cracking in the dirt to study biodiversity, and space probes are actively capturing the acoustic fingerprints of Mars. Modern technology is turning sound into the ultimate tool for exploration. So, as you study these formulas and facts, ask yourself, what hidden secrets of the entire universe will sound help us discover next? Keep questioning, keep learning, and I'll catch you on the next explainer.